So hello there and welcome to another tutorial. My name is Tanmay and today we're going to be talking about how you can train multi-label image classifiers without multi-label data, and in fact how you can do so with very little labeled data to begin with. Now before we get into that, I do want to say that if you enjoy this kind of content, you want to see more of it, please do make sure to subscribe to the channel, as it really does help out a lot, and turn on notifications so you're notified whenever I release new content like this. Like the video if you enjoyed it, and if you have any questions, suggestions, or feedback, leave it down in the comment section below, or feel free to reach out to me directly. My contact info is in the description. Now, diving right into it, effectively what we're going to do today is build a machine learning model that helps tell not only which dog breed is in an image, but if there are multiple dog breeds, which dog breeds are in the image. Now, we're going to do this with only a couple of labeled examples per class, and we have many classes. How are we going to do this exactly? Well, we're going to use a special kind of image classifier architecture. I haven't actually seen any research papers around this kind of architecture. This is something that I came up with for another project, although I'm reasonably certain that there must be other neural networks that implement something similar. And basically the idea is this. We take a very large pre-trained model. In this case, we're going to be taking ConvNext from Facebook Research. Specifically, we're going to be using the TensorFlow Keras version of this model. And what we're going to do is take all of our data and pre-extract a bunch of features from this classifier. We're going to use the convolutional neural network to get a bunch of image features for every single image that we have. Then we're simply going to train a multi-layer perceptron on top of those features to distinguish between the different classes in our data set. Now, what makes this special, what makes the training architecture special, is that we do not have one final layer where we slap on a softmax and calculate probabilities, because then we couldn't do multi-label classification. If you've got a golden retriever and a husky in one image, you wouldn't be able to determine that there's both. You would be splitting probabilities against the two, and the biases may not work out. You wouldn't get a good distribution. If you want to determine separately whether or not the golden retriever and the husky appears in the image, then here's what we're going to do. We're going to have a multi-layer perceptron. We're going to, modify the features a little bit. We're going to do some nonlinear transformations. And then we're going to take that new set of features and feed it into individual binary classifiers. Right, so what we're going to do is we're going to take that final set of features from the head of our network, and we're going to feed that into, say, for 10 different dog breeds, 10 different classifiers, each of which is trained on a binary objective as to yes or no, does the image contain this dog breed? Now, here's what's really interesting about this architecture. If you fed an image that does not have any dogs, then even without seeing any negative examples, the neural network should automatically be able to tell us that there are no dogs, because they've all been independently trained on their own binary objective, meaning that they would all naturally just say, no, this dog breed doesn't appear in the image, which implies sort of a negative category. But apart from that, if multiple breeds showed up in the image, then those classifiers, once again, would tell us which ones do and which ones don't, and the likelihood of that being the case. So it's a pretty interesting training architecture. We're going to be training on a Linux machine with two 3090 Ti's, which is kind of overkill because we're already extracting features from the images, but it's going to be very fast. So let's go ahead and take a look at how you can do that. All right, let's go ahead and take a look at the code, see how this model works and what it lets us do. Now, once again, the idea of the model is that we want to be able to train a multi-label classification problem. So, for example, given an image, we want to determine which dog breeds are within the image, and I prefer to do so without having to train the neural network on data that, for example, actually contains multiple dogs. What if I just had a folder, like I do here, with a bunch of folders that contain images of dogs, but only those individual dogs? So, for example, the golden retriever folder only contains pictures of golden retrievers, and the Walker Hound folder only contains pictures of Walker Hounds. Well, in that case, we can use the technique that I'm about to show you. This is the Stanford Dogs data set. I will link to it in the description below for you to go ahead and download it. It's free for everybody to use to build their own sort of neural networks and to research with. Each class has at minimum 150 images. However, just to make this a little bit more challenging, we're actually going to limit ourselves to using only 60 images total at most from any class. This does two things. First of all, it standardizes the number of images per class, which makes things easier. It also makes it so it's more challenging. We're only going to use 40 images for training and 20 images for testing for every class. So that's what our data looks like. Now, as you can see here, I've already prepared a little bit of code and some testing data, so we can go ahead and work with this data. So we start off at the very beginning of the pipeline. As I mentioned, we're going to be using features extracted from a neural network called ConvNext by Facebook. Now, ConvNext is a really interesting neural network. It beats a lot of vision transformers. It's really a very modern neural network, hence the name ConvNext. And I'm using the extra large version, which has a couple 100 million parameters, although this should work just as well on like the base model, so feel free to modify that according to how much compute power you have available to you. We cannot start a model like this one from scratch because we simply don't have enough images for it to get really good features to extract. So we will start off from a pre-trained model. So let's dive sort of into what this code looks like and how we actually work with the model. So the first script that I have over here is responsible for loading in all of the image data and simply using ConvNext to actually extract the features. Now, of course, in order to extract features, we need to load the model, but we need to do that multiple times across multiple scripts, not just extract. And that's why I have model.py. Model.py simply contains two functions. It has the getModel function over here, which enables us to load the actual ConvNext model. We actually don't need to print the model summary. We just need to call model summary for summary. So we have getModel over here that actually loads ConvNext using tf-keras. And we also have the getPreprocess function over here. This will return the preprocess image function that you're expected to call on your images in order to preprocess them for the neural network. So this includes basically center cropping at the 224 by 224, as well as running a standardization pass just to make sure that all the individual inputs, RGB, are within the range of the images that the neural network was originally trained on. So that's how this works. The pre-processing code is copied from the actual repo that does that contains ConvNext. So I can go ahead and close this, and we can go back to extracting features. So within this code over here, we start off by, of course, we have our imports, and then we get the preprocess function from the model script. Then I just have a function over here that loads all the different classes that we have. In this case, we effectively just glob data/star, so all the different folders within the data folder. I have a utility function for loading an individual image and then pre-processing it into a NumPy array. And then I also have another utility function that's responsible for loading an entire class. So what this will do is it will glob all of the files inside of that class's folder and only choose the first 60 files from the folder. Then it's going to go ahead and for each one, load those images, concatenate them into a single NumPy array, and then return them from the function. Then inside of our little main guard over here, to make sure that we're not running this code when the script is imported, all I do is I go ahead and get the model, the actual ConvNext model, and then I have a bit of an if statement. If I do pass a parameter to this script, then instead of actually putting together a data set, I actually take the individual parameter that was passed to the script, I assume it's an image, I load that image and save the embeddings. This is just a little utility that I've found that's useful because sometimes what I want to do is, for example, take a couple different images, simply embed them, maybe run like a PCA or something to do some dimensionality reduction and see where they land in the embedding space. So this is just a little bit of a utility. We don't actually use this for this example, but I thought it would be helpful if you would like to go ahead and extract the embeddings for an individual image. However, most of the time, you're not actually going to be passing any parameters. Instead, you're just going to move on to this section of the code. What this section of the code does is it goes ahead and loads all the different classes. So this is all of the all the different kinds of dogs that we're going to be classifying between. We load each class's images in. For every class, we run model predictions, and these predictions are the actual feature vectors that we get. These feature vectors are stored in a list. We go ahead and convert that to a NumPy array, and then we save all of the features that we extracted and all the different classes. These are the strings that were returned by this function over here. We save both of those into their own NPY files on the file system. And so, as you can see, I actually have those right here. And these files contain A for classes.npy, the name of all the different classes, and then for features.npy, it contains all of the feature vectors from the model. I can actually show you what that looks like by simply going into Python, loading up classes.npy. Oops. So if we were to go ahead and take a look at this, say if we looked at 5 of the values from classes, you see that we have the first 5 classes. This is just so we can keep track of which class index corresponds to which data folder. And then if I were to go ahead and load features.npy and just print out the shape, you can see that we have 120 different classes, which also checks out for the classes array. So 120 different classes. Each class has 60 images. Each image is described by a feature vector in a space of 2048 dimensions. So that is what that NumPy array looks like. It's pretty large, although at the end of the day, we end up dealing with, let's see here, about 57 megabytes worth of data. So not that much. So now we're gonna go ahead and actually train with it. So let's go ahead and see how we do that. Now this is, in my opinion, the interesting bit. This is where the magic happens, right? So we start off with our imports, of course, pretty simple, just NumPy and TensorFlow. Then I have a bit of a utility here for actually labeling data. I will get to how this works in just a moment, but effectively what this does is it puts together our inputs and outputs for Keras to be able to train with. So we'll get to this in a second, but first let's start off by focusing a little bit more on this function over here. This is really the secret sauce. This is the build model function. So this is effectively building the sort of head of the model. This is building the little bit that we're going to place on top of the feature vectors that we've already extracted in order to then further classify them into the individual dog breeds. So we start off with our input, which we know is a 2048 dimensional feature vector. And then we simply have 2 more layers. So we have one layer with 512 units, another layer with 256. So a 4x reduction. So we have like a fourth of the sort of size, and then a half of the size from there. Each time I do have pretty significant dropout. The reason I'm doing that is because we only have 40 images per class to train with, and there's a lot of feature vectors. And those feature vectors are really good, right? They are conv-next features, especially conv-next extra large features, which have been trained on a lot of ImageNet data. And what that means is that if you don't drop out, this neural network will very easily memorize a lot of your training data, which is not good. Now, to be fair, the feature vectors are generic enough that like even then you get pretty decent performance, but you get way better performance if you force this model to learn different paths through from the feature vectors to the classifications. So, and then of course we sprinkle in some layer normalization because that just helps with performance. Then I have another 30% dropout. Again, you can, what these exact probabilities are effectively hyperparameters that you can tune. I found that 0.3 works well here. So I'm gonna do one last dropout, and then we have 120 separate dense layers with 2 units each being activated by softmax that connect to this little bit of the head. The reason we do that is because, once again, the entire goal here is to have 120 separate binary yes or no classifiers for each dog breed to say, yes, this dog breed does, or no, this dog breed does not appear in the image. We group together all those layers into a list and then construct our model with one input, the feature vector, and 120 different output layers. We then compile that model to have 120 different sparse categorical cross entropy loss functions. We optimize with Atom, and we measure for accuracy. We print a model summary, and we return the model. Pretty dense code. From here on out, what we do is we simply go ahead and load the features. We could put together a training and testing set. The training and testing set is quite literally just train with the first 40 and then test with the remaining 20 because there's 60 total. Then we go ahead and build the model, we fit with the data that we're given, and we save. If you're wondering how this labeling function works, it's quite simple. In terms of the x, the input, that's just kept, as is. We simply take each individual NumPy arrays or each individual class's like input data, the image, and we just go ahead and put them all into a effectively flattened across the first 2 dimensions list. For the y's, though, for the output, it's a little bit more complicated. What we do is we make it so that for every class, we have to have a separate output expectation array. So for every class, we put together a list of what we expect the output to be, and then append that. However, it differs, right? So if we're currently putting together the expected output array for the class that we are currently looping through, then we go ahead and say, 1. We expect this to be 1. We want the yes, not the no for output. But if we're not currently putting together the expected output array for the current class, then 0, which makes sense because we want to make it so that, for example, when we're putting together the expected output array for a golden retriever, if we're not currently, using input images of the golden retriever, if j is not equal to I, then we don't want to say yes. So we use 0 as our no class, 1 as our yes class, and then we go ahead and convert those to NumPy arrays and return. This is not being converted to a NumPy array outside of the list comprehension because, again, when you have 120 different outputs in Keras will expect 120 different NumPy arrays of expected output being passed to it as a list. That is just what Keras expects. When you run this script, we end up saving the final model that we train as model.h5. Now, running this training script verbose is somewhat ugly, I will say, because when you do, you end up with, first of all, the model summary in and of itself is not the greatest, but even when you actually start the training process, you will notice that you have a lot of loss and accuracy values being printed. But if you were to sit here and sort of parse through it a little bit, I'm actually going to hit Control-C so we can stop it from moving. You start to see that pretty much immediately our accuracy values are very high. If I scroll up to the previous epoch here, if that's even something that's still here, yes it is, even our validation accuracies across all these different dense layers are nearing 100%. There is, of course, some level of error, but that's to be expected with the fact that, first of all, we're training a neural network. They're usually never perfect. Some classes may be very similar to others, and the fact that we're only using 40 training images to begin with. So it is a little bit ugly to run, but when you do run it, you end up with a model that is nearly perfect, and it's saved in model.h5, Keras's model serialization format. Now, we can run predictions. This is also another fun bit. The predict script is quite simple. We, of course, start with our imports and, of course, our script imports. I've also implemented another function to get the classifier model, which is the head that we're implementing on top. We go ahead and load conv next to get features, load the classifier model to classify on top of those features. I load all of the images that were specified as command line arguments to the script. We go ahead and extract all the embeddings, and then we go ahead and run the prediction against them. Once we've got the predictions, then we can go ahead and print them out. So we just loop through all the images that were passed in, once again, as command line arguments. We go ahead and print out the name of the image file. We load all the predictions from the NumPy arrays. And then I go ahead and load in all the different classes that we have, which, technically we could actually just do here, which would be more efficient. So once we have the list of the different string class names, we just loop through them. And if for that class, our prediction was, yes, this does exist in the image, then we go ahead and print. Otherwise, then we print yes. Otherwise, we print no. I have, however, effectively prevented this from happening by saying an elif false, so we don't get a bunch of no's. The reason I've done this is because we have 120 different classes, and if you were to feed in like an image of a golden retriever here, the problem is that you end up with like 120 lines, 119 of them being no, but only one of them being yes, and you can't find the yes. So if you'd like to revert this code to its normal state where it will do yeses and nos, then just change this to an else. Otherwise, that's effectively commented out by me saying else if false, because that's never going to evaluate to true. And then we just go ahead and print a new line separator for the next image. So we can invoke the script like so. What I'm doing here is I'm passing it an image of a golden retriever, an image of a German shepherd, an image that contains both a German shepherd and a golden retriever, and then finally an image of just a bunch of fields containing no dogs at all. Let's go ahead and take a look at what that gives us. Of course, we start off with initializing TensorFlow with all of its wonderful warnings. Convnext loads in, the classifier head loads in, and we run all of our predictions just like that. That was fast. Let's go ahead and take a look at what this means really quickly. We start off with a golden retriever. Of course, we see the only classifier, the only binary classifier that actually gave us a yes was the golden retriever classifier, which is exactly what we expect. Same thing with German shepherd. The only classifier that gave us a yes was the German shepherd classifier. Here's what's really interesting though. This entire model was never explicitly trained on, here's an image of both a German shepherd and a golden retriever. Well, the initial underlying model may have been, but our head was never exposed to that. Still, because of the training scheme, because of the training regime, we were able to determine that separately we have high confidences on both the German shepherd and the golden retriever categories. And what's even more interesting, in my opinion, is that we were able to take an image that does not contain any dogs and actually get the model to tell us that indeed there are no dogs in this image because none of the binary classifiers individually came back and said, here's a dog, or this dog does exist in the image, right? Now, there are some things to keep in mind. There are some potential pitfalls with the way that I've architected this training regime. One of the ones that immediately comes to mind for me is the fact that we are inherently introducing bias into the way that these classifiers see the data that we feed in. What does that mean exactly? Well, if we go back to the training script, you notice that whenever a classifier is classifying a no, the only reason it's ever classifying a no is because, well, of course, the dog that is associated with that classifier doesn't exist, but a different kind of dog does. The problem with that is that it's very possible that individual binary classifiers will not only associate the absence of their dog's features with a no, but also the presence of other dogs' features with a no as well. Now, that can be somewhat problematic for some use cases, because multi-label classification may somewhat suffer from that. I've personally found that it works well enough for my use case, especially because my primary goal when developing this model was to get an effective negative class, to know when no dogs appear in the image, versus a priority on multi-label classification. So sort of you get multi-label classification as an added benefit, but it's not going to be the best multi-label classification in the world because you are introducing some bias. Because once again, the no label for all these individual binary classifiers is not just the absence of what we want, but also the presence of other things that we don't. And that can be somewhat problematic. So even if, for example, you had an image with a golden retriever and a husky, it's possible that maybe the husky's no node was somehow, just in the right place in terms of the weight space to be negatively, or to rather for its no node to be positively affected by the presence of golden retriever features, since that was technically something it was trained on, an image that contained a golden retriever that it was trained to say no on. Now, ideally, its yes node should be more strongly correlated with the presence of husky features versus the no node's positive correlation with the presence of golden retriever features. However, I can't guarantee that because this is technically the training objective that we're giving it. So that's just something to keep in mind. I find that whenever you're training machine learning models, it is really difficult to keep track of all of this sort of bias that you're providing to the model, even when you don't intend for it to happen that way, right? Off the top of my head, I thought, this would work perfectly for multi-label classification, but when you really think about it, there are some pitfalls like this. So always keep that in mind when you're developing your machine learning models. But there you have it. That is a sort of training regime I came up with, enabling you to do negative classes or a negative class and multi-label classification using a pre-trained neural network and fine-tuning it on very little data. Really hope you enjoyed this tutorial. Once again, thank you very much for joining today. If you have any questions, suggestions, feedback, leave it down in the comments section below. Feel free to subscribe to the channel. It really does help out a lot. And turn on notifications so you're notified when I release videos like this one. Once again, thank you for joining, and goodbye.